Hello, I'm Hongil Kim from Korea University. Today, I'll be presenting our paper titled Universal Compressed Image Restoration via Codec-Aware Conditioning with Reinforcement Learning. Image compression involves various codec standards, including both traditional codecs and learned codecs. Even within a single codec, degradation varies significantly depending on their own compression level. Conventional compressed image restoration, so-called CIR, typically targets a single codec type. In contrast, universal CIR aims to handle images degraded by diverse compression methods simultaneously. The challenge in universal CIR is condition handling. Existing methods can be broadly categorized into implicit and explicit approaches. Implicit methods learn the degradation context internally without explicit supervision. Explicit methods directly utilize interpretable information, such as noise maps or quality level factors, as conditioning signals. However, both approaches have limitations. Implicit method can handle unlabeled data, but their capacity is limited when dealing with diverse codec types. Explicit methods perform well on labeled data, but fail on unlabeled data due to the absence of ground truth conditions, which restricts their applicability in real-world scenarios. Our goal is to address the limitations of explicit method in unlabeled settings. We propose a real module that maps unlabeled inputs to the closest labeled condition, enabling robust performance without ground truth label. Our framework consists of two training stages. Stage 1 trains the network using labeled data. Stage 2 fine-tunes the model for unlabeled data utilizing our proposed reinforcement learning scheme. Starting from the next slide, I'll explain the training details. The restoration network, which called RNet, follows a unit architecture. We introduce a codec-aware conditioning module, which called CCM. RNet is trained with a reconstruction loss in both stage 1 and stage 2. The CCM integrates the predicted probability vectors for codec type and quality level into the image features through an attention mechanism. Our policy network, which called PNet in stage 1, predicts these conditions. It takes an image as input and outputs probabilities for the codec type and the compression level. For label data, it is trained using standard classification losses. First, a cross-entropy loss for the codec type, and second, a cross-entropy loss for the compression level corresponding to the predicted type. For unlabeled data, ground truth labels are not available. Therefore, we adopt reinforcement learning to identify the optimal compression conditions. In stage 2, we jointly train both the policy and the value. The process is as follows. First, based on the policy network's outputs, we sample a specific codec type and level together with the corresponding value. Next, we compress the original image using these sample settings. Finally, we compute the SSIM between the input LQ image and the generated compressed image and use it as the reward. The value branch is trained to predict this sim-based reward, which helps stabilize reinforcement learning. In stage 2, we also fine-tune the type and level branches using reinforcement learning. We compute the advantage by subtracting this estimated value from the actual reward. Using this advantage, we optimize the policy loss to maximize the probability of actions that lead to higher rewards, thereby guiding the network toward the compression settings that are most visually similar. The final objective function of stage 2 combines three components: reconstruction loss, policy loss, and value loss. This combination enables effective adaptation to unlabeled data. our experimental results, and these results on label data D1 show that our method achieves performance comparable to the state-of-art explicit method DFPIR while outperforming implicit methods. Next, on unlabeled data, the two existing methods exhibit a significant performance drop. However, our method consistently maintains strong performance, effectively bridging the gap between labeled and unlabeled settings. This robustness extends to unseen data, DU. While existing methods fail to generalize, our proposed method consistently improves restoration quality. Qualitatively, our method achieves comparable or better performance than existing approaches on label data D1 and shows clear advantages on unlabeled D2 and unseen DU data by effectively removing artifacts. Additional examples on D2 and DU settings further demonstrates that our RL-based framework generates better results compared to the other methods. Thank you for your attention. Additional results such as per codec and per level analysis are available on our GitHub page, and please feel free to contact us via email for any questions.